Welcome to our exploration of psychrometry and the art of reading the psychometric chart. In this video, we will dive deep into how these charts serve as crucial tools in understanding and managing air and water vapor mixtures, which are fundamental for designing efficient and comfortable indoor environments. We will unlock the secrets of the psychometric chart, making it more accessible and practical for everyone, whether you're a student or a professional in the field of environmental engineering or HVAC systems. Let's simplify complex concepts and bring clarity to atmospheric thermodynamics. Psychrometry might sound like a complex term, but at its core, it's the study of the properties of air that affect temperature and moisture content. Understanding psychrometry is essential for anyone involved in creating comfortable and sustainable indoor environments. In psychrometry, there are two primary measurements that are crucial: dry bulb temperature, dB, which is the air temperature that you would typically measure with a regular thermometer. It represents the actual air temperature of the environment. And wet bulb temperature, WB, that is measured with a thermometer that has its bulb wrapped in a wet cloth. The wet bulb temperature is always lower than or equal to the dry bulb temperature, and it reflects the lowest temperature that can be achieved through the evaporation of water. Both measurements help us to determine the state and behavior of the air around us, which is foundational in fields such as HVAC, weather forecasting, and environmental control. When we talk about the dry bulb temperature, or dB, we're referring to the standard temperature reading that most of us are familiar with. It's the straightforward, everyday temperature that you might check before heading out for the day. This is the same temperature you hear from the weather forecast on the TV or see on your weather app. It indicates the air temperature without taking into account the moisture content in the air. For many of us, this is our daily reference for how hot or cold it feels outside. Now, let's explore the concept of wet bulb temperature, or WB. Imagine taking a thermometer and quickly dipping its bulb into water so that tiny droplets cling to it. What do you think happens to the temperature reading on this thermometer? Intriguingly, the wet bulb temperature will be lower than the dry bulb temperature. This occurs because the moisture on the bulb evaporates, and evaporation is a cooling process. The energy required to turn water into vapor is taken from the heat in the air around the bulb, thus lowering the temperature indicated by the thermometer. This measurement is crucial, particularly in scenarios where the effects of humidity and evaporative cooling are significant. It helps us understand more about how moisture in the air influences our environment and temperature perceptions. A psychrometer is a fascinating instrument used to measure both dry bulb and wet bulb temperatures, giving us a clear picture of the air's moisture content. Let's delve into its workings with the help of two illustrations. In the first picture, imagine dry air at a temperature of 25 degrees Celsius entering a space where a wet bulb thermometer reads 15 degrees Celsius. This temperature difference occurs because the air isn't fully saturated with moisture and can absorb water from the wet bulb. As the water evaporates, it absorbs heat from the air, leading to a drop in the thermometer's reading. Now, look at the second picture where the scenario changes. Here, air that is 100% saturated at 25 degrees Celsius flows past the wet bulb thermometer. Notice that the thermometer also shows a reading of 25 degrees Celsius. Why is this? In fully saturated air, the air cannot hold any more moisture, meaning there's no evaporation from the wet bulb, no absorption of latent heat, and consequently, no drop in temperature. This brings us to an important conclusion. When the air is fully humid or saturated, the dry bulb and wet bulb temperatures will be identical. These visuals not only demonstrate the mechanics of a psychrometer but also underscore the critical relationship between air temperature, moisture content, and saturation. Understanding this relationship is essential for interpreting psychometric charts accurately and applying this knowledge in real-world situations. Now, let's explore the fascinating world of psychometric charts, indispensable tools for understanding the properties of moist air under various conditions. These charts provide a wealth of information, allowing us to analyze and interpret key parameters: water content, WC, or moisture content, MC, or humidity ratio, HR. These terms all refer to the amount of moisture present in the air relative to the mass of dry air in a given volume. Relative humidity, RH, expresses the percentage of moisture in the air relative to the maximum amount it can hold at a given temperature. Vapor pressure, Vp, measures the partial pressure exerted by water vapor in the air. Dew point, dP, marks the temperature at which the air becomes saturated and moisture begins to condense into dew or fog. Enthalpy, H, reflects the total energy content of the air, including both sensible and latent heat. Think of it as the heat required for heating or cooling a given air mass. By mastering the interpretation of psychrometric charts, we gain valuable insights into the thermal comfort, humidity levels, and energy requirements of various environments. These charts serve as indispensable tools for HVAC engineers, building scientists, and anyone involved in designing or managing indoor environments. Dry bulb, dB. This is the regular, everyday temperature we're accustomed to measuring. On the chart, it's represented by vertical lines extending from the x-axis. On our chart, you can find the dry bulb measurements here. Wet bulb, WB. Unlike dry bulb temperature, wet bulb temperature considers the cooling effect resulting from water evaporation. It's plotted along the saturation line, specifically at points where it intersects with the dry bulb temperature. On your chart, the wet bulb temperatures are along the last curve. Dry air has a greater capacity to vaporize water, leading to more pronounced cooling effects. This is why wet bulb temperature tends to be lower than dry bulb temperature, reflecting the cooling influence of water evaporation. Understanding how to interpret dry bulb and wet bulb temperatures on the psychrometric chart is essential for accurately assessing air properties and designing effective HVAC systems. A couple of more key elements of the psychrometric chart. Saturation line. This line represents the point at which the air becomes saturated or 100% humid. It's like to the pressure versus temperature line that we discussed in an earlier session. Remember, as temperature increases, vapor pressure also rises. This line forms the basis of psychrometric charts. Relative humidity, RH, indicates the percentage of actual water vapor in the air compared to the maximum possible amount at a given temperature. It's calculated using the formula RH equals vapor pressure divided by saturated vapor pressure times 100. Notably, RH lines mirror the shape of the saturated line. When the air reaches saturation, RH hits 100%. Now, let's explore additional elements depicted on the psychrometric chart. Humidity ratio, HR, also referred to as specific humidity, absolute humidity, water content, or WC, or moisture content, or MC, is the ratio of water present in a mass of air. It's calculated as the mass of water, in grams, per kilogram of dry air. On the chart, HR is represented by horizontal lines originating from the saturated line. On this chart, you can read the moisture content measurements here. Dew point. This marks the temperature at which condensation occurs. While it can be approximated using the formula where T is the dry bulb temperature in Celsius, more accurate for RH greater than 50%, it signifies a crucial point for understanding air moisture content. On this chart, you can find the dew point measurements here, or you can continue the horizontal line of moisture content to the left until you hit the RH 100% curve, and read the temperature dew point from the wet bulb numbers. Here is an example. If it is 25 degrees Celsius outside, what is the relative humidity if 1 kilogram of air is holding 14 grams of water? By connecting a vertical line from 25 degrees of dry bulb at the bottom of the chart, and a horizontal line starting from 14 grams per 1 kilogram of dry air moisture content, we find a point that shows the relative humidity in those conditions, which is 70%. Now, if we draw a line along with the wet bulb temperature lines, we can find the air's wet bulb temperature on the RH 100% line, which is 21 degrees. It is a good practice to find as many properties of the moist air as we can, with the two pieces of information that is given to us. Can you tell with this moisture content, at what temperature will it start to rain? Remember that it rains when the humidity is 100%. We are basically asking you about the dew point. Use the same technique that we explained earlier, and you will see the dew point, the temperature in which it rains or the condensation happens, when relative humidity or RH is 100% and moisture content or MC is 14 grams per 1 kilogram of dry air, is almost 19 degrees. Let's look at another example. A room at 35 degrees Celsius initially contains 40 kilograms of dry air, meaning zero moisture in the air. If 1 liter of water spills onto the floor and eventually evaporates into the air, what is the resulting humidity ratio? Here, we want to calculate the humidity ratio HR, or the moisture content MC. 1 liter of water is exactly 1 kilogram. So when the spilled water evaporates into the air, we have 1 kilogram of water or moisture in 40 kilograms of dry air. That means that 1 kilogram of air contains 25 grams of water or moisture. Now if an air conditioner begins to cool the room, how cold can the room get before condensation begins to form? Again, with the same technique to find the dew point, we can find out that the condensation will happen at almost 28.5 degrees Celsius. Enthalpy, H, serves as a crucial metric in thermodynamics, representing the total energy within a system. Its calculation considers 2 primary factors. First, temperature change, the energy required to alter the temperature of a substance. And second, expansion work, the work performed as the material expands and exerts pressure against the surroundings, typically at constant pressure. In HVAC contexts, enthalpy signifies the heat needed to be added or removed to achieve a specific temperature. This understanding is vital for optimizing HVAC systems and ensuring efficient thermal management. Enthalpy lines on the psychrometric chart serve as valuable indicators of energy content within air parcels. Here's what you need to know. Enthalpy lines typically run parallel to wet bulb lines across the psychrometric chart, aiding in the visualization and analysis of energy distribution within air masses. Enthalpy is measured in kilojoules per kilogram, in the metric system, providing a standardized measure for assessing energy levels within the air. On this chart you can find the enthalpy measurements here. By understanding the placement and significance of enthalpy lines, engineers and HVAC professionals can make informed decisions regarding temperature control and energy management in various applications. Let's calculate how much heat is required to heat air with a dry bulb temperature of 19 degrees and a wet bulb temperature of 15 degrees to a new dry bulb temperature of 35 degrees Celsius. Assume no more moisture is added, which means that the moisture content MC remains the same. On the chart, by locating the initial conditions of the air we can find out that the moisture content is 9 grams per 1 kilogram of dry air and the enthalpy is 42 kilojoules per kilogram. With the same moisture content and the new dry bulb temperature of 35 degrees, we can measure the enthalpy at 57 kilojoules per kilogram. That means that the energy needed to be given to the air by heating it is 57 minus 42, which is 15 kilojoules per kilogram. Here is a more advanced example. In the picture, you see a very simple diagram of an air handling unit. The conditions of the intake air, point A, and the return air, point B, along with their percentage of the total flow are indicated. Use the chart to predict the supply air conditions, point C, after the mixing of the 2 air streams. The first step to solve this question is to find the location of point A and point B on the chart, given the properties of each stream. Then we draw a line that connects point A to point B. Point C, which we want to find, is on this line. By looking at the 2 input streams we see that stream A makes up 80% of the total flow. That means that the conditions of the resulting stream, or point C, is closer to the point A by 80%. In fact, if we divide the AB line into 5 equal pieces, point C is 1 piece or 20% away from point A, and 4 pieces or 80% away from point B, so the approximate conditions of the resulting stream or point C can be located on the chart too with a very good estimate. Let's have an example about one of those window-mounted air conditioners. Outside air is being passed through an air conditioner before being supplied to the room. What is the humidity ratio, or moisture content, of the air? Given the conditions of the incoming air indicated on the picture, and using our psychrometric chart, the moisture content can be measured at 18 grams of water per kilogram of dry air. At what temperature will water start to condense? Our dew point here will be around 23.2 degrees Celsius. How much water will condense, per hour, if the supply air is 22 degrees? To solve this part, let's look at the initial conditions of the air, or the input air, which according to our calculations has the moisture content of 18 grams per kilogram of dry air. The air is cooled to 22 degrees Celsius and humidified 100%, so then with the use of our chart, its moisture content can be measured at 16.5 grams per kilogram of dry air. That means that per each kilogram of dry air the moisture is reduced from 18 grams to 16.5 grams. So the change in our moisture content is 1.5 grams per kilogram of dry air. Knowing that the flow of air is 20 kilograms per hour, and the amount change in the moisture content, we can calculate the mass of water being condensed per hour by multiplying the two numbers, which gives us 30 grams per hour. How much heat being removed by the air conditioner? Again, by comparing the initial and final conditions of the air, we see that the enthalpy or heat content of the air is reduced from 77 kilojoules per kilogram to 64 kilojoules per kilogram. So, the change in enthalpy or heat content is 13 kilojoules per kilogram. How much power is this? Let's remember the relationship formula between power, enthalpy, and the flow. Power is delta H, change of enthalpy, multiplied by the flow. Therefore, power is 13 kilojoules per kilogram, change of enthalpy, multiplied by 20 kilogram of air per hour, which is 260 kilojoules per hour. Since 1 hour is 3,600 seconds, our power then is calculated to 0.072 kilojoules per second, or 72 joules per second or 72 watts. And that's a wrap on our journey through psychrometry and psychometric charts. By understanding these fundamentals, you're better equipped to tackle HVAC challenges with precision. Keep exploring and applying what you've learned, and you'll be well on your way to mastering the world of air conditioning design.